All right, let's jump right in. We're going to talk about a tool that completely changed the game in modern biology, the polymerase chain reaction, or PCR. Now, this is a technique that has totally transformed everything from medicine to forensics, and the whole story starts in a place you'd probably never expect.
So, picture this. It's late one night in 1983. A scientist named Kary Mullis is just driving down a winding California highway. And then, out of nowhere, bam, one of those classic eureka moments hits him. He literally pulls his car over right there and starts scribbling down an idea that would, no exaggeration, change the world. That was the moment PCR was born.
And you know what's wild? How fast this whole thing took off. I mean, look at this timeline. He has the epiphany on the highway in April of '83, and by the end of that same year, he'd already run the first successful experiment. Less than 10 years later, the patents get sold for $300 million. And then in 1993, Mullis gets the Nobel Prize for it. The impact was just massive and immediate.
Okay, so what was this revolutionary concept that he dreamed up on the side of the road? What exactly is PCR?
Honestly, the absolute best way to think about PCR is like a molecular photocopier. Its genius is all about power and precision. PCR can hunt down one tiny, specific piece of DNA. We're talking like finding a single sentence in an entire library of books, and then just copy it, over and over and over again until you have millions or even billions of identical copies to work with.
So how does it do it? Well, it works in this simple three-step cycle that just repeats. First up is denaturation. You just heat the DNA up, and that heat unzips the classic double helix into two separate single strands. Then, step 2, annealing. You cool things down a bit, which lets these tiny things called primers come in. Think of them like little molecular bookmarks that latch on to the exact start and endpoints of the DNA section you want to copy. And finally, extension. A special enzyme gets to work, building a brand new matching strand of DNA right between those two bookmarks. And here, you can really see that cycle in action. You've got that initial DNA strand, and it goes through those 3 stages: heating, cooling, and copying. Then the machine just does it all over again. And the key thing to notice is that with every single cycle, the amount of DNA you're interested in just doubles.
The power here is just exponential. It's kind of mind-blowing when you think about it. You start with one single copy. After one cycle, you have 2. After 2 cycles, 4. Then 8, 16, 32. You let this process run for, say, 40 cycles, which only takes a couple of hours, and that one starting molecule has mushroomed into billions of copies. It's an absolutely incredible amplification engine.
Now, what's really cool is that the story doesn't stop there. The technology evolved. You see, standard PCR gives you a pretty basic yes or no answer to the question, is the DNA I'm looking for in the sample? But a more advanced version, called qPCR, that's quantitative PCR, it goes a huge step further. It doesn't just ask, is it there? It asks, okay, but how much of it is there? It actually counts the copies as they're being made in real time.
So how on earth does it count the DNA? Well, qPCR cleverly adds fluorescent dyes into the mix. So as more DNA copies are made, more of the dye latches on, and the whole sample literally starts to glow brighter. A machine measures that brightness after every single cycle, and what you get is a real-time plot just like the one you see here. That red line shows you exactly when the sample's glow crosses a certain threshold. The faster that curve shoots up, the more DNA you had to begin with. It's as simple as that.
Okay, so we've got this incredible machine that can find, copy, and even count specific bits of DNA with pinpoint accuracy. So what? What can you actually do with all that power?
Well, one of its most famous jobs, we use it to solve crimes.
Here's the key thing you need to know for forensics. All of us humans, we share 99.9% of our DNA. But that tiny little 0.1% that's left over, that's what makes each of us totally unique. And forensic science zeroes in on these specific spots in our DNA called short tandem repeats, or STRs. These are just little bits of DNA where a short sequence gets repeated over and over again. The exact number of repeats is different for pretty much everyone, creating a unique genetic fingerprint. And how do you analyze these from a teeny tiny sample found at a crime scene? Well, you guessed it. You use PCR to make millions of copies first.
So this is basically the modern forensic workflow in a nutshell. First, you get your sample, and you extract the DNA. Then, and this is the magic part, step 2, you use PCR to amplify those unique STR regions. After that, Another process separates all those copied fragments by their size. And finally, you can visualize the whole thing as a unique pattern of peaks. That's the DNA profile.
And this is the moment you always see on the crime shows, right? You take the DNA profile from the evidence at the crime scene and you compare it to the profiles from your suspects. You lay the patterns side by side and you can see it clear as day. The profile for suspect 2 is a perfect match. Bam! It's PCR that makes this kind of slam-dunk evidence possible from the tiniest, most impossible-to-see traces.
All right, let's just do a quick recap. So, remember, PCR is your molecular photocopier. It works in a super simple 3-step cycle to turn one copy of DNA into billions. That core idea then grew into even cooler tools like qPCR that can actually count DNA in real time. And of course, it's the absolute foundational engine that drives all of modern DNA fingerprinting and forensics.
It's just an amazing story, isn't it? An idea that hits you during a late-night drive becomes this Nobel Prize-winning technology that redefines entire fields of science. The real power of PCR is in its beautiful simplicity. Find, copy, and repeat. It's just a powerful reminder that the next world-changing idea might not be some super complicated thing, but a simple, brilliant insight that's just waiting for its own highway moment. So it makes you wonder, what will the next epiphany unlock for us?